Hello. In previous two lectures, we explained the basic concept of semaphores and a very influential problem, the dining philosopher's problem. In this third lecture, the focus will be on three classical problems. The producer-consumer problem, also referred to as the bounded buffer problem. The writer's problem, and finally, the roller coaster problem. You will learn a significant number of skills in solving problems in synchronization using semaphores. Each of these problems illustrate a few important concepts that are very frequently used in real applications. So let's talk about the producer-consumer problem. As we mentioned earlier, the producer-consumer problem is also referred to as the bounded buffer problem. This problem was discussed in Dijkstra's seminal paper, actually his lecture notes for his course. This is the original version. The printed version is published here. And this version is publicly available on the internet. So the producer-consumer problem goes as follows. Suppose we have a circular buffer of n slots. Here, for simplicity, we represent this circular buffer as an array. But of course, you could use whatever data structures. Say a linked list, a circular linked list. And each cell here, or each entry here, is good for storing an integer. In reality, it may be a data structure. We have two pointers in and out. The in pointer indicates the first empty slot for you to add information into. The out pointer indicates the location for you to retrieve the next item. Therefore, it's like a first in, first out. So this is the structure. A producer thread keeps adding things to the location at in. A consumer thread keeps retrieving information out of the location out. Of course, after the producer added something to this location, we have to move the in pointer to the next location. By the same reason, after a consumer successfully retrieving information out of the out location, the consumer must move the out pointer to the next one. So this problem is very simple. So think about our computer system or your daily life. Are there any situations that are similar to this producer-consumer problem? I hope you pause for a while and think about it and jot down your answer on a paper. So please, if it is possible, pause. Now, if you'll come back, I'm sure you probably have figured it out. Several examples you are used to with your computer system. For example, we talk about STD in so many times. You open a window, you type something through stdin for your program to read. And stdin has a screen buffer associated. Then when you type in something through stdin, you are the producer. Each stdin buffer has a limited number of entries. You press a key, that key press will be recorded in the stdin buffer. And your program, which reads something out of stdin to be processed in your program, is a consumer. By the same reason, consider std out. Your program prints something to the std out buffer. And std out buffer, of course, would have a finite number of positions. So you print the characters one by one to the std out buffer. And in the system, there is a program that connects between your std out and the screen. When one line completes, that complete line will be shown on the screen. So in this case, your program switches its role from a producer to become a consumer. Then the program that shows you the contents you stored in the std out buffer to the terminal window is a consumer. Therefore, in this way, a thread or a process could be a producer at one moment and then switch to consumer sometime later. So this role could be switched back and forth so many times. Now, actually, when you want to print something to a printer, your program does not print directly to the printer. As you know, the system has a printer queue. Your file, your output file is printed to a printer queue. So in this case, the printer queue would have a limited space allocated on a disk. So when you print, your program is a producer. The printer queue is the bounded buffer because there's a limited space. Then when you indicate that my file is going to be printed on which printer, the printer server would become the consumer that takes a printed file stored in the printer queue and printed to the indicated printer. You should be able to find so many examples in daily life. For an example, if you call your friend and your friend has a voicemail or an answering machine, voicemail and answering machine has finite capacity. It could only store a limited number of messages. So when you call your friend, and what if he's not there? So you leave a message. So the answer machine of your friend's phone is the buffer, a bounded buffer because the size is limited, and you is the producer. When your friend becomes available, he checked his voicemail or answer machine and finds out, okay, there are messages there. In this case, your friends become the consumer. And then he may want to answer your call, but you are not there. So he becomes the producer. Your voicemail or your answer machine is the buffer, and you changed change its role to become a consumer. So think more about it. So the producer-consumer problem is so commonly seen in daily life and in computer systems. So let's analyze this very general problem. As we mentioned, a producer always adds things to the location pointed to by the in pointer. Let's say the buffer is represented by an array buff in, and the consumer always retrieve the contents from buff out. Of course, we mentioned in and out must be advanced after depositing and retrieving. In is shared among all producers. Why? Because two threads or two processes could add information to this location. So not in order to make sure that only one process or one thread could add information, in has to be protected, allowing only one thread that could access to in. So here we have a mutual exclusion situation. By the same reason, out is shared by all consumers. Of course, not all producers would want to add, not all consumers would want to retrieve. But as long as there could be multiple uh, producers who may access in or multiple consumers who may access out, then we have mutual exclusion situations. Not only this, recall whatever the program you wrote in the past years. Some bugs always appear at certain condition which you missed. Many people refer to this condition as the boundary condition because it lies in the boundary between correct and incorrect. So if you write your program and are always able to find these boundary conditions and write your program defensively, that is, you address all of these boundary conditions so that your program is always in the correct path. Your program is more robust. So in this problem, what are the possible boundary conditions? I could quickly name two, and I am sure you could do the same. So if the buffer is full, no producer could add information into the buffer, right? If the buffer is full, then every element is here, and the in and out would be at the same location. So if you allow the producer to add information into the buffer, this new information would override the first available information to be retrieved and pointed at by out pointer. So this is something you have to take care of. The first boundary condition is if the buffer is full, producer must be blocked. Until what? Until the buffer has an empty slot. Now the second boundary condition is if the buffer is empty, you should not allow a consumer to retrieve information. If the buffer is empty, in and out will point you to the same location. And if you allow that consumer to retrieve an information pointed to by the out pointer, what that consumer would get is garbage. So in this case, a consumer has to be blocked if the buffer is empty until the buffer is not empty. So examining examine these two boundary conditions again. Remember, if the buffer is full, no producer can deposit. And if the buffer is empty, no consumer is allowed to retrieve. But the question is, a producer could continue only if the buffer is not empty, right? But who makes the buffer not empty? Think about this. Of course, this who has to be a consumer. For an example, if a producer is blocked due to the buffer being empty, then when a consumer comes, this consumer, of course, can retrieve the information out of that buffer. Instantly, after retrieving this information, the buffer is no more full. Isn't it that this consumer has to inform a waiting producer, allowing that waiting producer to go in a symmetric way? If a consumer is blocked because the buffer is empty, then when a producer comes in after depositing his information, this producer has to inform a waiting consumer, indicating that you can go. So the complexity of this problem is not about how we are going to protect in and how we are going to protect out. It is the communication between the producers and the consumers. So let me reiterate. Producer cannot proceed if the buffer is full until a consumer retrieves some information, and that consumer must inform a waiting producer so that that producer can go. By the similar reason, if there are consumers waiting because the buffer is empty. So after a producer adds information to the buffer, that producer must inform a waiting consumer, indicating that, okay, you can go. So this is the whole story. A simple, not so complex problem, but has a important way or important pattern to illustrate the use of notification. Now, let's put things together. Again, I draw a diagram here. A red square means I may have to wait. A green circle means something has happened. If this red square is a semaphore wait, then when someone is going to open or signal the semaphore, we use a green circle. And the blue line relating this wait and this signal. However, semaphores are not only to be used as lock. Semaphores are very frequently used as a way to implement notification. So in this case, if a thread is waiting, not due to a lock, then what this waiting is for, it means this thread is waiting for an event to occur. So another thread who causes that event to occur notifies a waiting thread so that that waiting thread can continue. Therefore, a red square means a wait for an event to occur or a lock. A green circle indicates if it is a mutex lock, it is a signal to open that lock, allowing the next one to enter the corresponding critical section. And if a thread causes an event to occur, that thread must notify those other thread waiting on that event, and that is indicated as a dashed arrow. So let's analyze the producer first. When a producer comes in, it waits for the buffer to be not full, as we mentioned earlier. Now, if the buffer is not full, the producer can continue. Continue to do what? To do deposit. So we consider the whole buffer, including the in pointer and out pointer as a single unit for protection. That just make our life easier. So let's say the whole buffer and in and variables in and out are protected in a critical section. And that critical section is protected by a semaphore with initial value 1. Therefore, this producer, after knowing that the buffer is not full, and proceeds to lock the buffer. If he is successful, this producer is the only thread that is able to access that buffer. So the deposit activity is in the critical section corresponding to the buffer. Then, after deposited, this producer unlocked the buffer, allowing the next producers or the next consumer to proceed. Now, after adding a item into the buffer is definitely not empty. Therefore, the event corresponding to buffer being not empty happens. As a result, the producer informs a waiting consumer to proceed. After that, the producer comes back and try the next run. Then let's take a look at a consumer. A consumer must wait if the buffer is not empty. And if the buffer is not empty, then the consumer proceeds to lock the buffer. If the locking is successful, the consumer could retrieve the information out of the buffer. After that, the consumer unlocks buffer for the next guy to use. Who could be the next guy? It could be a producer or a consumer. Then, because the consumer has already retrieved a piece of information, the buffer is definitely not empty. Therefore, the event that is associated with buffer not full, happens. Therefore, the consumer notifies a possible producer there, indicating now the buffer is not full. So here we have the critical section. We have the critical section here. This critical section is protected by the same semaphore here. This semaphore and this semaphore is the same. So a producer could be blocked here, and because the buffer is not full. At the same time, the buffer may not be empty. For example, suppose the buffer has 4 elements, And there are two elements there. Therefore, the producer would find out the buffer is not full. At the same time, and the producer could proceed, at the same time, the consumer would find out the buffer is not empty. So the producer can also proceed here. But the same buffer is protected by a single semaphore with initial value 1. Even though we have multiple producers and multiple consumers could proceed to this locking the buffer activity, only one of them can proceed. In that way, we guarantee there is no more than one thread, whether that thread is a producer or a consumer, would have a chance to access the buffer. Now, after adding something, the buffer is definitely not empty. So the producer notifies the consumer. And after the consumer retrieves something, the buffer is no more full. This consumer notifies the producer. As a result, you will see that we need 3 semaphores. The first one is for protection purpose to establish mutual exclusion. We need one more semaphore to indicate the buffer is full or not. If the buffer is not full, we allow a producer to go. If the buffer is full, a producer must be blocked. By the same reason, we need a semaphore to block consumer if the buffer is empty or consumers are blocked. And if the buffer is not empty, we allow some consumers to proceed. Of course, when the producer notifies this semaphore, and if there's no consumers waiting there, then this semaphore counter value is simply increased by 1. And if a consumer, after taking out something and notifies this semaphore indicating that the buffer is not full, there could be no producers waiting there. In this case, this semaphore's counter is just increased by 1. So I hope you review this diagram and understand what I said. And if you still have some confusion, please go back and watch this probably 5 to 8 minutes again before we proceed to explain the code. So if you will, please pause. Now, this is the solution. We need 3 semaphores. Let's take a look at this one. Semaphore mutex has initial value 1. It means mutex is to be used to build mutual exclusion. Now, initially, we assume that the buffer is empty. Nothing is stored there. We use the semaphore not empty to block consumers, because initially nothing is in the buffer. Therefore, initially all consumers must be blocked. How would you do that? You simply set the initial value to 0. Hope you understand this. Now let's forget about the initial value for the other semaphore not full for now. The semaphore not full is used to block producers. When the semaphore is full, producer will be blocked here. Because initially, the buffer is empty. Therefore, it's clear that the initial value for not full should not be 0. So what the correct initial value should be will be discussed very soon. Now let's say a producer comes in and check to see is the buffer full. If it is not, this producer does not have to wait. So it proceeds to the next in order to lock the buffer. If this producer successfully locks the buffer, this producer adds information into the in location and advance the in pointer. Because this is a circular array, we use the modulo arithmetic. Then this producer signals the mutex semaphore indicating I'm done. The next one could come in. And finally, the producer reaches the last statement, the signal call. The producer signals not empty because the producer just added information to the buffer. As a result, the buffer is no more empty. And therefore, the producer simply signals not empty, so that one of the consumer waiting here could proceed. And for this consumer, if he is released, he proceeds to lock the buffer, retrieve the information, advance the out pointer, and release the critical section. And finally, because the buffer is no more empty, therefore, this consumer signals the semaphore not full, indicating now the buffer is not full. One of the waiting producers, if there's any, could continue. So this is very simple. It completely reflects the diagram. So let's say, what should be the initial value of not full? If the initial value of not full is 1, then only one producer can pass through and deposit and signal. And only one consumer can get through not empty. And then finally signals not full, allowing the next producer to go. Now recall, we discussed a very interesting example. 2 threads printing 1, 2, 1, 2, 1, 2. So if you initial not full to be 1, you're actually writing a program to like a printing 1, 2, 1, 2. So you are enforcing a particular deposit and retrieve pattern. Producer, consumer, producer, consumer, producer, consumer. I hope you understand this. So this is not very efficient and actually not a good solution at all. So if 1 is not good, 0 is definitely wrong, of course, because you force the producer to wait and the system cannot proceed. Then 1 is not so good. How about 2? A 2 would generate some randomness because 2 producer can pass through not full, although there's only 1 can access the buffer. So when this one signal, when this one exit, this consumer signals, and the third producer could come. So in that case, we have some randomness. Now, if you could use 2, you could use 3, 4, and 5, right? So here, what is the maximum good value for not full? I would say that is the buffer size. Remember, n is number of available slots. So in this case, you actually have a countdown lock. You allow n thread to pass through not full dot wait. And if we have more than n processes, well, the remaining would be blocked here. So these n processes would compete to get into this critical section and eventually notifies a possible consumer. So if you have n plus 1, it's an overkill because you have no way to allow n plus 1 thread to go into this critical section without waiting. For example, you have allowed n process to pass through not 4, and what if all n of them add things into the buffer? Now, after the nth process signals, assuming none of the consumers are there. So not 4 is n. Now, not 4 from n minus 1. Now, after n processes finish this, the value of n, the counter of the semaphore, is reduced to 0. Now, if the initial value of not 4 is n plus 1, you actually allows the n plus 1 thread to go. This n plus 1 thread would override the first deposit information. Please think about this. So this is your first rather simple example. Now, here is a question. Previously, we have not full here, not empty here. And we have, what if we moved mutex weight outside and mutex signal outside? In other words, the intention of this code is we lock the buffer first and wait the buffer to be not full. That's for the producer. And add information there, signal a consumer, and then unlock the buffer. So what would happen? Please think about it. The answer is you could immediately get the deadlock. So please use an execution sequence to generate a deadlock from multiple producers and multiple consumers. And you may just use one, the size 1, that is, the buffer has only 1 slot. Okay, please do it as an exercise. Now, the next example, the readers-writers problem is a bit more complex. And there are so many subtleties here. So please listen carefully. And if you are not ready, you may pause and return to this lecture later on. We have 2 groups of threads. One group is referred to as readers, the other, the writers. The readers and writers could have access to a shared resource. And you know, when you see accessing a shared resource, race condition could happen. You are right. But many applications do not need this very restricted mutual exclusion requirement. So here are the rules. This shared resource allows the reader to read simultaneously. That is, all reader can read. And this is very reasonable because reading things out of a resource, shared resource, does not harm that resource. Everybody would just get the same data. But we only allow one writer to write at the same time. When a writer is writing, no reader can read, and that's extremely important. If there are only readers reading, it's fine because they don't change the contents of that shared resource. When a writer is writing, that writer will change the contents of that shared resource. The complication, so writer has to be mutually exclusive. Now, the third bullet tells you the complication. When a writer is writing, no reader can read. Of course, if a writer is writing at the same time, you allow the reader to read to the same location, it is very likely the reader will get incorrect results. We have seen this kind of example multiple times. In particular, this is referred to as concurrent sharing. So this rule makes the problem a bit more complex. We have to establish something more in order to make the whole thing workable. That is, if there is any reader reading, all incoming writers must wait. And this is very reasonable because writer could overwrite the information currently is being read due to concurrent sharing. So we have a race condition. Therefore, if there is any reader reading, no writer should write. So as long as there is a reader reading, all incoming writers must be blocked. This is referred to as the reader priority version. Reader priority version means as long as there is a reader reading, no writer can write. So from the previous analysis, we know we need a semaphore to block the first reader and the writers if a writer is writing. Here's the magic word is first reader. Why? We'll mention that. But anyway, writer has to be mutually exclusive when it is writing. Therefore, this semaphore must be there in order to block either reader when a writer is writing and the incoming writers when a writer is writing. So when a writer arrives, it must know if there are readers reading, right? We mentioned on the previous slide, if there are readers reading, writer must wait. This is the reader priority version. Therefore, if there are readers reading, writers must be blocked. Then how do we know whether there are reader reading? The easiest way is you have a counter. You have a counter. When a reader comes in, we add 1 to it. When a reader finishes his reading, subtract 1 from it. So we have a counter. So this counter definitely is increased and decreased by readers. Let me call it reader count. This reader count is accessed and modified by readers. As a result, we need a semaphore to establish mutual exclusion. We need 2 semaphores, 1 for blocking writers, and if there are writer writing, we block the readers. Why 1 is enough? That is very subtle to be discussed later. As we mentioned, this is the reader priority version. It does have a big problem. Very unfair to the writers. What this problem is, if the readers keep coming in an overlapping way, waiting writers have no chance to write. Let's take a look at this diagram. So a reader comes in, reader 1 comes in. While this reader is reading, a writer wants to write. But because there is a reader reading, writer has to be blocked. Now, before reader 1 completes its reading, reader 2 comes in. So at the end of reader 1's work, this writer cannot be released because reader 2 is reading. Before reader 2 completes the work, reader 3 comes in. So after reader 2 finishes, this writer cannot start. So if this pattern goes on and on, this writer could be starved. It has no chance to read. Well, this could be theoretical, but as long as it could happen, it will happen. Murphy's Law. So let's analyze this. Now, I divide this discussion into multiple slides. Each slide illustrates one subtlety. As we mentioned, when a reader comes in, it has to add 1 to the reader count, indicating one more reader. If it is a first reader, it has to wait until no writer is writing. Now, this is the magic word. If this reader, the just coming in reader, is the first one, it must check to see, is there a writer writing? If there is a writer writing, this first reader must block itself. After that, this reader can reach data. After finishing reading, decreases the counter. Now we have one more step there. Because the reader controls the reader count variable. The writers may not know it. Therefore, just like the last customer, please turn off the light. So if upon exit, if this is the last reader, this last reader must tell some waiting readers or writers that no reader is reading. So this is what the reader is going to do. So here we use a semaphore to establish mutual exclusion in order to protect the reader count. Here you can see this is a release of the semaphore. Okay? And then we have a semaphore here. The same semaphore. This semaphore is used to block writer if there is a writer writing. Now, if there is a writer writing, then all subsequent writer will be blocked here. If when a writer comes in and no writer is writing, this writer could go ahead. And after finishes it, the writer releases lock. By the same reason, I am the reader. If I am the first reader, I check to see, is there a writer writing? If there's no writer writing, I simply go down. We will talk about later. If there is a writer writing, I'm blocked here. So this semaphore is used to block all subsequent writers and the first reader if there is a writer writing. Okay, so this explains these two semaphores. Then, as we mentioned, this semaphore is used to block if there is a writer writing. This semaphore is used to block the first reader and all subsequent readers. Are blocked here. Now let's see why. This is a lock, mutex lock. So suppose this is the first reader. So because this is the first reader, he has no difficulty to pass this mutex lock. Then keep this in mind. This mutex lock is used to protect the reader count. So this first reader add 1 to the count and check to see, am I the first one? If I am the first one, then I have to check to see, is a writer writing? If there is a writer writing, I'm blocked here. So this first reader is blocked here. Now, look at very carefully. This reader goes through the first mutex lock. Increase count if it is the first one. And if there is a writer here, this first reader is blocked here, while it still has the mutex lock. So if the first reader is blocked here, all subsequent reader would be blocked here. Now let me quickly go through it again. Hopefully you could follow me without any trouble. Suppose this is the first reader. It has no trouble to get through the reader count semaphore. Increase it by 1. Am I the first? If I am the first, I have to make sure there's no writer writing. So I go down here. This is semaphore to block readers, the first reader and the writer, if there is a writer writing. Now, if there is a writer writing, I am here. Now look at this path. Get the lock here, here, and I get here. If I am blocked here, I still have the quick mutual exclusion. Because I haven't been able to signal. Therefore, this lock is still locked. So if there are other readers coming in after I get through this lock, they will be blocked here. So in this case, this semaphore, as long as it is able to block the first reader, it is able to block all subsequent reader so that none of the reader can read. So this is a direct block. If there is a writer writing, and this is an indirect block that could block all subsequent readers. Now, this first reader is blocked here. If the current writer finishes writing, this current writer signals the semaphore. So if this first reader is lucky, this reader goes back to its normal execution path and signals the mutex lock. At the same time, this reader reads the data. The second reader could go through because this second reader is no more the first one. So the second reader simply goes through and we have a concurrent reading here. So it doesn't matter which reader could go fast or finish fast. That reader must decrease the reader count. So lock the reader count, reduce the reader count, and then am I the last? And so on. This will be discussed later. Here, the key points is if there is a writer writing, a new coming writer will be blocked here. And if there is a writer writing, the first reader would go through here, here, and here, and blocked here. Once the first reader is blocked here, all subsequent reader will be blocked here. So if this is not the first reader, which means there are reader rating. So this guy just add 1 to the counter because I am not the first one. I simply release the lock and start reading the data. Now, I hope you could pause here for a while and understand these two annotations fully. Then we move on to the signal part. As we mentioned earlier, when a writer finishes writing, the writer signals this semaphore. Keep in mind, this is the same semaphore. So this signal could release a writer or the waiting first reader. Remember, this semaphore is used to block the first reader and or subsequent writer, if currently there is a writer writing. So if the writer signals the semaphore, this signal could release the next writer, or it could release the first reader. We don't know which one will be released because the semaphore waiting set is not ordered. If a writer is released, that writer continues. And if the first reader is released, that first reader returns its normal execution path, released the protection for reader count, allowing the second reader to come in. And then no matter what, each thread, after reading, it has to decrease the reader count. So lock the reader count again, reduce the reader count, and then, am I the last? As I mentioned earlier, it's equivalent to say, the one who leave the room last, please turn off the light. So if I am the last, I simply signal this semaphore. If there's no one waiting, fine, just adding one to the counter. And if there are someone waiting, this signal could release a writer or the first reader. Okay, so think carefully. My question is, this signal comes. As I mentioned, this semaphore blocks the first reader and the subsequent writers. When this signal comes in, what exactly the thread would be released? The writer or the first reader? Please think very carefully. The answer is obvious if you follow these two slides carefully and thoroughly. If you cannot get it immediately, no problem, just pause and watch it again. So if I am the last one, I signal releasing someone here, and then release a lock, and then I come back to do the next round. So this version of the readers and writers problem, that is the reader priority version, put all the burdens on the reader to increase the count, to release the writer, decrease the count, to release the writer, and so on. So this is the complete set of annotations for the reader. Please review it carefully. Then the writer is so simple. The writer competes to get through the semaphore. If it could, then it writes. And then release the semaphore and come back. So the writer is very simple. Now, before we go to coding, please review these several slides and understand you know the interaction between the readers and the writers and the use of all semaphores. In particular, the use of the semaphore. It blocks the first reader and the subsequent writers. And why we have am I the first one and am I the last one here? Okay, if you want, please pause. So this is the code. we need a semaphore mutex with initial value 1 in order to establish a critical section to protect the reader count. Initially, its value is 0. And we did a semaphore to block the first reader and all subsequent writers if there is a writer writing. So translating the diagram to a program is rather straightforward. This is a critical section. This is a critical section. When a reader comes in, it locks the reader count semaphore at 1 jot. And if the reader count is 1, it means I am the first reader. I block here. If I am not the first reader, this part would be skipped. And then we simply release the mutex, allowing the next one to come. Because if I am not the first one, there are reader reading. And reading can be done in a simultaneous way. So if I am the first one, I wait until to be released by this write mutex call, signal call by the writer, or this write mutex signal call by the last reader. But which one? This is the exercise I asked you to think about earlier. Then I can read the data. Upon exit, lock the semaphore for protecting reader count, subtract 1 from it. If I am the last one, then I signal this semaphore. And then released mutex and I'm gone. So for the writer, it just keep looping, wait for the access to the shared resource and the write and come back and release it and come back and so on. Keep going and going. So this is pretty easy for the writer, but it takes some time for you to understand the reader part. So this is the solution for the reader priority problem. And this actually was the first solution published in the first proper published paper discussing the writers problem. Later, we will encounter several different solutions to the readers and writers problem so that writer starvation could be overcome. Then let's talk about the third classical problem. Well, this problem is actually not so classical. But I picked this problem here is it illustrates something interesting. This is usually referred to as the roller coaster problem. Suppose in an amusement park, there is a roller coaster car. This car can hold maximum C passengers. And there are impossible passengers wandering around in the amusement park. So C is much smaller than the number of passengers. The car can go around the track only when it is full. That is, only if every seat of the passenger, every seat of the car has been occupied. Then the car can start. After finishes a ride, each passenger gets off the car and wandering around before they return to the roller coaster for next ride. And then, due to safety concerns, the car only rides 3 times and then shut down for maintenance. So that's pretty simple. But if you think deeper, there are some communication problems. In reality, it won't happen. But in your program, if you're going to write a program for that, it could happen. What are these so-called boundary conditions? First, the car always rides with exactly C passengers. Cannot be C plus 1, cannot be C minus 1, and so on. Now, no passengers will jump off the car while the car is running. You might say, that is ridiculous. Yes, in real world, nobody would do that because it's committing suicide. But in your program, if your program is not written carefully, a passenger threat could jump off the car while the car is running. And no passenger would jump on the car while the car is running. While the car is running, in reality, it's not possible unless you are the Superman. So no passenger will request another ride before they get off the car. That is, when the car is full capacity, seating C passengers, the car starts running. While the car is running, no one on board that car can jump off. No one on the ground can jump on. When the car stops, every passenger must get off the car so that the car becomes empty. Then the car would accept the next batch of C passengers. So those who were riding on the car must get off the car and re-enter the queue for the next ride. So this is simple, but how to control this two may require some thinking. So here is a description of the passenger here, the car here. So a passenger decides to have a ride and joins the queue. We have a queue here. If the car is not there, everybody must wait. On the other hand, when the car is ready for the next batch of passengers, the car must tell the passenger so that they could start boarding. So let's assume that we have a gatekeeper here. This gatekeeper knows whether the roller coaster car is parked safely and empty in the station. So when the car is ready for boarding, this car simply tells the gatekeeper that, okay, I'm there. You could allow passenger to be on board. So a passenger make a decision, I want to take a ride and join the queue. And this queue is managed by a gatekeeper, which can be considered as a semaphore. Okay, this part is pretty easy because you just set the semaphore value to 1, allowing one to go or something. Or you could also set this semaphore up as a countdown lock, say allowing C passenger to pass through. It's your choice. Then, when the car informs the gatekeeper that, okay, I am ready, you could allow the passenger to go. So this gatekeeper in the solution to be presented has the initial value of semaphore to be 0. So all passengers who want to take a ride will be blocked. So the passengers would be allowed to go one by one. We only allow C passengers to get through this gate. So each passenger must go through this check-in one by one. Because we allow checking one by one, it means this is a semaphore whose initial value has to be 1. Of course, you must allow the first passenger who gets through this gate to check in, so the initial value has to be 1. So here we allow C passenger to get through. So here, the first passenger gets in again. The last one leaving the room, please turn off the light. So we allow each passenger to go. So when the first passenger comes in, am I the last one? No, I just have a seat. Now I simply allow the next one to go. So the next one, check in. Am I the last one? No, I simply release the lock and have a seat. Now, what if I am the last passenger? If I am the last passenger, I take the responsibility to inform the car here so that the car could start running. Now, look at the car. When the car is ready for boarding, the car informs the gatekeeper, and the car is blocked. Blocked for what? Blocked for loading. So if the last passenger is here, then the last passenger informs the car, saying that I am the last one, everyone is on board. So the last passenger comes back to the normal path and release the lock. Now, if we only release C passenger from here, well, that's no big deal because this semaphore returns to 1. Okay? So here we check in one by one. If I am the last one, I inform the car that I am the last one, everyone is on board and have a seat. You could start the engine. And then finally, after the car's engine started, the car started riding. Now, it's very interesting. We said no one can jump on board. Of course, if you are here, you have no way to jump on board. You are blocked by this semaphore. This semaphore only allows C passenger to get through. So those who are not on board would be blocked here. Now, how can we guarantee that those who are on board would not commit suicide? Here, once you get through your check-in process, you have a seat. You have a seat. This seat is definitely a semaphore. So this red square is a semaphore. You are blocked here. Meaning, if I, after the last one, signals the car, this signal allows the car to run. So while the car is riding, all C passengers are blocked here. Because they are blocked here, it means they cannot jump off the car. So when the car finished a cycle, the car stops. So we see we have a notification here telling a passenger sitting in the car, please get off. And this passenger, after gets off, tells the car that I am gone, bye-bye. And the car signals the next one. So the passenger gets off the car one by one. A passenger could get off the car if the car tells him to do so. But the one who gets off the car must inform the car that I'm gone, you are able to kick the next one off. Then the passenger plays for a while and come back for the next run. So this is for the passenger, even though our discussion is mixed passenger and car activities. Now, let's take a look at the car. I hope you are not bored because we have already discussed. So the car comes in, indicating it's ready. It means the car tells the gatekeeper that please stop admitting passengers. And of course, the passenger would be checked in one by one. So while the passenger is checking one by one, the car is blocked for loading, passenger loading. And then when the last passenger is in the car, this last passenger informs the car that all passengers are on board. The car starts a ride. While the car starts a ride, all passengers are blocked by this semaphore. So after riding, the car waits until all passengers are off. The car sends the passenger off one by one. And then the car goes back for the next run. So this is what the car has to do. So before we get to the code, please review the several slides. I try to make sure that all related activities are shown in a coherent way. Okay, please stop if you want. Now, let's take a look at the code. We need a queue serving as the gatekeeper. Initially, its value is definitely 0, for sure. Now we need a boarding semaphore in order to block the car while passengers are boarding. And we have a semaphore to block all passengers on board to simulate riding. Initial value, definitely 0. Now, we have another unloading semaphore. When the car tells a passenger saying that, please get off the car. This is done in a one-to-one manner. So after telling a passenger to get off the car must wait for that passenger's response indicating I am off. You may get to the next one. So the queue semaphore, the boarding semaphore, the riding semaphore, and the unloading semaphore are all initialized to 0. And we have a semaphore for check-in. Check-in semaphore, you must allow the first passenger to check in, otherwise you have a deadlock. So its initial value is 1. So the passenger is pretty easy. When a passenger comes, join the queue that is blocked by the gatekeeper. If this passenger is allowed to go, going through the check-in and add 1 to the counter. If the counter is equal to the maximum, that is full loading, I am the last one. Then I tell the car saying that boarding has finished. Then I release the check-in semaphore and then blocked by the riding semaphore, indicating now I am on the car and enjoy the ride. Then when I am released from this wait, released by whom? Released by car, indicate the car has stopped. Then I'm released from here, so I get off the car and say bye-bye to the car driver or the station manager by signaling unloading here. Once right after signaling me on the semaphore riding, the manager will stop there so that he will wait until I am gone safely. Then he come back to signal the next one. So this is the passenger. Now for the car driver or the car, it iterates number of rides. As we mentioned, only take T rides for maintenance purpose. The car has to be shut down. So we set the count to 0 because the count will be increased by 1 by passenger. Then the car signals the gatekeeper maximum number of times, and that is the capacity C. So this loop would allow C passenger to get through this queue. And then the car wait for boarding. When the last passenger signals boarding semaphore, the car can go. So here, all passengers are on board and we could start it right. So you could use whatever way to simulate this riding. And finally, when the car stops, the car signals one passenger and asks him to get out the car safely. After the passenger gets out safely, the passenger waves his hand to the manager saying that I am done. So the manager is allowed to allow the next one. So this for loop release all passengers on board. So study this code before answering a few simple questions. Now, my first simple question is, count is being shared by car and the passenger threads. In the passenger thread, we project count by the check-in semaphore. But why? In the car thread, the variable count is not projected. Think about it. The answer is rather easy. Have you figured it out? If you haven't, consider this. When the car thread initializes count to 0, there's no passenger running because all passengers are blocked here. So that means initializing the variable count is carried out before a possible passenger to add 1 to it. So in this way, we do not have to lock the count. So this question is pretty easy to answer. Now, exercise. In this code, the car and the passenger interact in a one-by-one way. Is this necessary? Will you be able to come up with a different way? The second related question is, I signal this, and the passenger signals back. Can unloading be removed? That is, we remove this line and at the same time, this line. This question is a little bit more sophisticated. So why don't you, after watching this lecture, remove this line and remove this line and see what would happen with execution sequences. You may just use 3 passengers and 1 car. So far, we have completed our discussion on 3 classical problems. Let's do a very short and quick summary. We have learned a few tricks in this component: lux, countdown lux notification, the dining philosopher problem, and 3 classical problems. That is, very often from these 3 classical problems, we often use a counter to indicate whether certain condition is met. For an example, in the readers-writers problem, we need a reader count. In the roller coaster problem, we have a check-in and boarding count. So a counter is frequently used. And sometimes thread may have to be paired up. That is, one guy from group A and the other guy from group B, they must be paired up in order to jointly finish a task. And this is what we have learned in the roller coaster problem. And please, you have learned so many examples, simple and complex. Please use this basic and frequently seen patterns to solve other problems. The next few lectures will discuss patterns, but so far you have learned enough to do your program assignment 4. Now, let's get back to a very important issue with respect to the use of semaphores. In your program, if you use many semaphores, it could mean thread execution will be locking and locking, unlocking, locking and unlocking. There will be so many locking, unlocking activities, or waiting, signaling, waiting, notification, waiting, notifying, and so on. So the more of this locking, unlocking, and waiting, notifying activity, it means your program is not very efficient. So it's just like you drive in a big city, especially in a downtown area. You just step on the accelerator. Few seconds later, you have to brake, waiting for pedestrian or red light. And then right after you start and accelerate, you meet the next red light. So this is very similar to you stop because a red light is locking. And you start and proceed is unlocking. So you have so many locking and unlocking. It's just equivalent to go through a very busy city street. You will encounter so many red lights and you encounter red and green, red, green, and so on. Very inefficient. Now, the other opposite would be if you use just very few semaphores. That is, you lock something, you are going to do a very large critical section before you unlock. So that means each semaphore for critical section, when you lock a critical section, you're going to do a lot of jobs before you unlock. What is the problem? The problem is so simple. You lock a critical section for a long time. Then you are sure that many people would be, many other threads will be blocked by the wait. As a result, other threads may have to wait for a long time to get into the critical section. So very many semaphore is inefficient. Very few semaphore, with each of which is a very large critical section, is also very inefficient because thread may be blocked by semaphore for a long, long time. So you have to have some compromise. When you do your programming assignment, try your best to minimize the number of semaphores in your program, and at the same time, reduce the length of locking time. That is, make your critical section as short as possible. If semaphores are used to block for an event, then make sure that event will happen very soon. Otherwise, there will be many threads waiting on that semaphore in order to get that event happens. So this will be good for this lecture, a little bit long. The next lecture will be semaphore patterns and pass the baton pattern. So let me stop here. See you next time. Goodbye.